that will produce like a background, just like a rolling ripple of gravitational waves through the universe. And it's going to look kind of like this in the pulsar data, these red bands. So just sort of like a kind of slow modulation in the residuals. And you know, maybe this could be in any one of these pulsar data plots. We really can't tell because it would be really low level and really hard to pick out. However, before I do that, these are more residuals. This is for the international data set. The point of showing this is just to show these are all different pulsars. Each one of these names here, these numbers here, this is like a pulsar calling card. The numbers tell us where it is in the sky. The different colors are different telescopes. This is time. So we have all this pulsar data for all of these pulsars, and we're searching for these gravitational wave signatures in all of them. And it's really hard. It's really, really hard. And the reason it's hard is that we're not like LIGO. We don't have a telescope like on the Earth, right, where we can just tweak our gravitational wave detector. Our pulsars are in space. We can't travel to one of the pulsars, and we can't adjust it or measure it or dip a spoon into it and see what it's made of. And so there are all these other things that are happening. Like for instance, the pulsars themselves, this is a cartoon of a pulsar. They have all these different layers. They're not perfect rotators. There might be some noise in the pulsar spin that looks like gravitational waves. And how do we tell them apart? Well, what we do is we are looking for a very special signal. So what this plot shows, this is the Earth. These lines go out to all our different pulsars. And we are looking for a correlation as a function of the sky separation of the pulsars that's predicted exactly by general relativity. And let's see what that looks like. So Einstein tells us that if there are no gravitational waves, we shouldn't see a correlation, a spatial correlation in the sky between the arrival times, right? Some of them might be late or early, but it shouldn't depend on the sky separation. With gravitational waves, we should see a very special correlated signature. So for pulsars that are in the same direction, they should have correlated signatures. If they're separated by like 90 degrees, there should be an anti-correlation. And up here, we should have a correlation. Let's just look at this in another way before I go back to the results. So here are two pulsars in the same direction from the Earth. When a gravitational wave passes, if one arrives early, the other will arrive early. These are two pulsars separated by 90 degrees. If one arrives early, the other will arrive late. And at 180 degrees, we expect a correlation again. Do people know what correlation means? It's kind of a sciencey term, but it just basically means if things have a positive correlation, the same thing is happening to the pulses, and if it's negative, a different thing is happening. And because of gravitational waves, the way they work, this quadrupolar thing, we expect this dip at 90 and these peaks at 0 and 180. And it's a very special signature on the sky that we wouldn't expect from any other thing. And, sorry, let me go. Oh, okay, it's okay, it's all good. So now let me just talk a little bit about our data, and then I'll show you our big result. So the way NavGrav works is we make data sets. So we started in 2005, and then every few years we put out like a new set of data with all this timing on all these pulsars. And our first data set had 17 pulsars. These are pulsars along this axis. Our next data set had 37. The data set after that had 45. The next one had 48. And our most recent data set had data on 68 pulsars. So we keep growing the number of pulsars in the data set. We're always searching for new pulsars in the sky. Searching for pulsars is really, really important. And in the most recent data set, with 68 pulsars, we saw some very interesting results. So let me just go back to two data sets. This was our 11-year data set. This was 4 years ago. What this shows is the correlation. These black points are the correlations that we see on the sky. And this blue dotted line shows the correlation that we expect if there are gravitational waves. Does it look like these black points are matching that blue dotted line? Does it look like a good fit? How many people think it's a good fit? No one. It just looks like noise, right? So we did this analysis again, a year and a half later. These are our 12-and-a-half-year results. The black points look better. The sizes of these errors, these bars here are error bars. The errors have gone down. Do they look like they're matching that blue curve? Maybe a little bit more, but not really. It doesn't look very convincing, right? Like, maybe these sort of are looking at it, this point's way off, and I don't know, no one will look at this and say, oh look, you've made that detection. The exciting thing though, is that even though we didn't see this curve, we did see a source of like common noise that we thought was gravitational waves, and I'm not going to go into these plots at all. I'm just going to say these show properties of the noise, and our colleagues in other pulsar timing arrays around the world saw noise with the same properties. And so we thought the noise was gravitational waves in this previous data set, and we were very excited, but we didn't see these correlations, so we couldn't say for sure it was gravitational waves. And so what we did is we got together with our international colleagues, and we all said, this is very exciting. Let's organize ourselves and all look at our next data sets to see if we see these correlations in them. And this was really very exciting because we published 18 papers from all these different pulsar time array collaborations, all on the same day, June 29th of this past year, all announcing the results of our most recent analyses. And this is what NACRF saw in our most recent results. No, sorry, it's the first time I'm doing it with this like remote clicker. There we go. Okay, does that look like it's matching that blue curve? Yes, it does. And so, it's so hard for me to explain this, I think, like to explain the excitement of this to a general audience, because I'm sure you're looking at this and you're like, what is this even? Like they're just yellow points on a plot. But we have been looking for this signature for 15 years. We've been looking for correlations that peak here, are negative here, and positive again here. And when we saw this, we were very, very excited, because this can only be due to gravitational waves. And so we could say for sure that that noise we saw in previous data is actually gravitational waves, which is really, really exciting. And I was surprised a lot of newspapers and magazines really picked this up and ran with it. It's kind of a, hard to understand esoteric results, but we've got all these great headlines like scientists say space-time churns like a choppy sea, monster gravitational waves spotted, and scientists found ripples in space and time and you have to buy groceries. That was my favorite. Okay. So let me talk a little bit about what we think these are. This is a very detailed plot for probably like the two astronomers in the audience, so just ignore this. If you're not one of those people, it just looks like, well, it's very detailed. But I wanted to show it because you might wonder, how can you tell what these are, right? Like you see this correlation. What's producing them? Is it black holes? Is it something else? What we do is we look at something called a spectrum. So we look at the amount of power in the gravitational waves versus gravitational wave frequency. And this blue band is our measurement of the spectrum. And this dotted line here is what we expect for supermassive black hole primaries, for monster black holes at the cores of galaxies. Do these lines look pretty similar? They look pretty similar, right? So that's very exciting. We see this evidence for gravitational waves, and then it matches the source that we think is producing them, these supermassive black holes. So we think it's probably supermassive black holes. We can't say for sure yet, but what we're probably seeing are black holes at the cores of galaxies like this. As these galaxies are merging together, they're producing these very bright gravitational waves that have very long periods or low frequencies in our frequency band. And we can do things like this. We can try to place constraints on how galaxies come together. So if we have two different models for galaxies, one with isolated binaries, one where they're interacting with like gas and stuff in their environment. Here's our nanograph results, and we can say, hey, this model, oops, sorry, I keep meaning to click the red thing and press the other button. We can look at it, we can say, okay, this model is disfavored with respect to this model here, this blue model, because our results line up a little bit better with that blue model than with that orange model. So this means we need more binaries, massive binaries, binaries with more interaction. This is just a little cartoon, but the idea is we can start to say things about how galaxies come together. And I'm almost done. The interesting thing, though, is that we can't say for sure it's due to these monster black holes, because there's all these other models that can also produce gravitational waves. There are things called cosmic strings, which are basically like defects in space-time. They also should produce gravitational waves. They might look a lot like what we're seeing. We also could be seeing gravitational waves from the very early stages of early universe inflation, like right after the Big Bang. So there's all these models. There are hundreds of papers already since our paper in June, but all these theoretical physicists with all these crazy models for what these gravitational waves are. So how will we know that for sure what we're seeing is from a supermassive black hole binary at the core of a galaxy? Well, one way is if we can detect an individual source. So what I've shown so far, that curve we're seeing, we think that's due to a background, just all the signals from all the binaries added up together. But soon, maybe even within the next few years, we'll be able to detect gravitational waves from individual sources. So this is a galaxy called 3C66b. This is a radio optical image, and it has these jets. And from looking at the motion of these jets around the galaxy, we think there are two very massive black holes at the core that we should be able to see in our pulsar timing data. And here's this guy right here, this 3C66b galaxy. This is gravitational wave frequency. This string thing is like how bright the gravitational waves are. This curve shows the sensitivity of the International Pulsar Timing Relay in 2025, just in 2 more years. And it's sitting above the curve. So that means we might be able to detect gravitational waves from this particular galaxy in only a couple more years. All these other dots are other binary systems, and some of those are above this curve too. So this will be really, really exciting. What it'll mean is that we can start to understand the processes of how galaxies come from separations like this to separations like that, and how these black holes come together at the cores. This is actually really important because we think that this process of galaxies merging with other galaxies is how galaxies like the Milky Way were born. The first galaxies were small, they were kind of funny